Imagine standing inside a sun-baked mud-brick home in the middle of the Nile Valley 4,000 years ago, where the external heat climbs well above 115 degrees Fahrenheit. Sweat stings your eyes as heat ripples across the blinding desert sand. There are no fans. There is no electricity. Yet, when you step through the narrow entryway into the deepest chamber, the scorching air vanishes, replaced by a sudden, shocking chill that feels almost supernatural. How was this possible without a single machine? The truth goes back thousands of years, and it is far stranger than you think. For generations, modern society has viewed ancient life through a lens of quiet pity. We picture our ancestors suffocating through ruthless summers, trapped inside dark, stagnant rooms, hopelessly waiting for nightfall to bring relief. We assume that before the invention of mechanical compressors and chemical refrigerants in the 20th century, human beings were entirely at the mercy of the climate. But that assumption is completely wrong. When you look closely at how ancient civilizations survived in the hottest places on Earth, you realize they were not helpless at all. They were master thermodynamicists. Without formal physics textbooks or modern instruments, ancient Egyptian builders solved the challenge of extreme heat through sheer observational genius. They manipulated air pressure, harnessed radiant physics, and exploited fluid dynamics to turn their living spaces into self-sustaining cooling engines. What we call modern air conditioning is simply a noisy, energy-hungry mechanical substitute for architectural intelligence that ancient builders perfected 4 millennia ago. To understand how they pulled off this miracle, you have to look at the very soil beneath their feet. In the late 19th century, pioneering British archaeologist Sir William Matthew Flinders Petrie began excavating the ancient Egyptian worker town of Kahun near the Fayum oasis. Kahun was built around 1890 BCE to house the artisans, stonemasons, and laborers constructing ancient Egyptian monuments. What Petrie uncovered was not a haphazard cluster of primitive huts, but a meticulously planned urban center engineered with environmental precision. The houses were constructed with exceptionally thick walls made of Nile River mud mixed with straw and sand, dried under the blistering sun. At first glance, a heavy mud brick wall seems like a simple, crude choice of building material. But in thermal physics, mud brick possesses an extraordinary property known as high thermal mass. During the peak hours of the day, when the sun beats down relentlessly on the outer surface of the wall, the heavy mud brick acts as a giant thermal sponge. It absorbs the extreme external heat energy very slowly. The heat does not pass immediately through to the interior of the home. Instead, it moves through the dense material at a sluggish crawl, a phenomenon modern architectural engineers call thermal lag or phase shift. By carefully calculating the thickness of the mud brick walls, ancient builders engineered a precise 12-hour delay. Throughout the entire scorching 14-hour daytime shift, the heat creeping inward from the sunlit exterior never reaches the inner living quarters. The inside remains astonishingly cool and stable. Then, as night falls across the desert and ambient temperatures plummet dramatically, the mud brick walls begin releasing all that stored daytime heat inward and outward into the cool night air. The house essentially warms itself through the chilly desert night, resetting its thermal battery completely by sunrise. Have you ever wondered why modern concrete homes feel like ovens at night? It is because modern thin construction lacks this balanced thermal lag, trapping heat at the worst possible time. But delaying heat was only the first half of the equation. To truly cool an environment below the ambient air temperature, ancient Egyptians needed to actively remove heat from the atmosphere. They did this by mastering the physics of evaporative cooling. When liquid water transitions into vapor, it absorbs kinetic heat energy from the surrounding air molecules, causing the temperature of the air to drop instantly. In wealthy Egyptian villas as well as humble worker homes, occupants hung heavy linen sheets soaked in Nile water directly across open doorways and narrow window slits. As the dry, hot desert breezes blew against the building, The air was forced to pass through the damp fabric fibers. Water evaporated rapidly into the dry air, stripping away heat energy before the air could enter the room. This simple trick could drop the air temperature inside a hallway by up to 15 degrees in a matter of minutes. An even more sophisticated application of this principle involved porous earthenware vessels known as qulla, or zir. Ancient Egyptian potters specifically crafted these unglazed clay jars so that microscopic pores remained throughout the clay walls. When filled with water, tiny droplets seeped through the porous clay to the outer surface of the vessel. The dry air sweeping past the jar evaporated these outer droplets continuously, drawing heat out from the core of the jug. Not only did this process provide icy drinking water in the middle of a desert summer, but strategically placing clusters of these moist jars in narrow corridors created localized drafts of cold, refreshing air. In the late 20th century, renowned Egyptian architect Hassan Fathi conducted rigorous scientific testing on these traditional passive cooling methods. Fathi demonstrated that a single large, moist terracotta jar placed in an airflow pathway could generate the cooling equivalent of a small, modern electrical air conditioner without consuming a single watt of power. Yet, the true masterpiece of ancient Egyptian environmental engineering was not just water or mud. It was their ability to capture and command the wind itself. In the scorching settlements of the Old and Middle Kingdoms, builders noticed that breezes traveling high above the ground were significantly cooler and cleaner than the dust-choked air near the baking desert floor. To harness these high-altitude winds, they invented the malqaf, an architectural windcatcher that remains one of the greatest feats of passive design in human history. A malqaf was a tall tower or raised roof scoop oriented precisely toward the prevailing north winds, known as the Etesian winds, which blew steadily down the Nile Valley. As cool breeze swept over the rooftop, the angled scoop of the malqaf intercepted the moving air and funneled it down a narrow vertical shaft directly into the heart of the home. As the air was compressed inside the narrowing shaft, its pressure increased and its speed accelerated, driving a fresh, cool current deep into the lowest chambers of the house. When archaeologist Dr. Mark Lehner led excavations at the lost city of the pyramid builders near the Giza Plateau, his team discovered clear structural evidence that ancient builders intentionally arranged residential complexes to optimize wind flow and natural ventilation. The alignment of streets, court walls, and roof openings formed an interconnected aerodynamic system. Fresh air was systematically directed through living spaces, picking up internal moisture from wet courtyard mats before escaping through small, high-level exhaust openings on the leeward side of the building. This movement was driven by another fundamental law of physics, the stack effect. Warm air inside the house, heated by human bodies and cooking fires, naturally rose toward the high ceiling. Because warm air is less dense, it exited through small, clear-story windows positioned near the top of the walls. As this rising warm air escaped, it created a low-pressure zone near the floor, which actively sucked in cool, moist air from the malqaf windcatcher and shaded courtyard garden. The result was a continuous, passive air exchange system that operated day and night. Air moved steadily through the home, constantly evaporating moisture, removing stale heat, and maintaining a comfortable microclimate without a single moving mechanical part. The house itself acted as a living, breathing respiratory system. When you step back and look at the whole picture, the ingenuity of ancient Egyptian air conditioning challenges everything we think we know about progress. Today, we rely on heavy industrial grids, noise-polluting compressor units, and power-hungry technology to keep our indoor spaces comfortable. When the power grid fails during a modern heat wave, our glass and steel towers rapidly become unlivable hotboxes. Ancient Egyptians, operating 4,000 years ago with nothing more than mud, water, clay, and wind, built homes that were immune to heat waves. Their air conditioning was not a luxury appliance tacked onto a wall. It was baked into the very architecture of their world. They did not try to fight nature with raw power. They studied its rules and crafted spaces that worked in harmony with the environment. The next time you adjust your thermostat or hear the hum of a modern compressor unit, remember that your ancestors solved the exact same problem thousands of years ago, using only thermal mass, evaporative cooling, and wind capture. Imagine standing inside a sun-baked mud-brick home in the middle of the Nile Valley 4,000 years ago, where the external heat climbs well above 115 degrees Fahrenheit, and realizing that the ancient past held the secret to the future all along.